Let's solve the polynomial inequalities graphically. Up first, f of x is greater than 0. Another way of thinking about this is asking where is the function or the graph above the x-axis? Where is it above 0? And that's going to be in this first region here. And our answer is going to be in terms of domain, so x values, -4 to -1. We'll use parentheses due to the strict inequality, the greater than 0. We don't want to include those x-intercepts. The graph is also above the x-axis here, from 3 to positive infinity. So we'll do union, parenthesis 3 to infinity. Notice in example B, it's very similar to A. This time, f of x is greater than or equal to 0. So we're asking where is the function above the x-axis or on the x-axis. So it's very subtle. The only difference is we can now include those x-intercepts. So we'll bracket the -4, bracket the -1, bracket the 3, infinity stays a parenthesis. In example C, we have f less than 0. In other words, where is the graph below the x-axis? That's on this first piece here. Again, your answer is in terms of domain or x values. So that is from -infinity up to -4, parenthesis. Again, parenthesis on the -4 because we're looking at a strict less than. We'll union that with the other interval, which is from -1 to 3. That region is also below the x-axis. -1 up to 3, parenthesis. D is very similar to C. It's subtle. Be careful when looking at questions like this. This time we're asking where is the function below or equal to the x-axis. So we can now include x-intercepts. -infinity up to -4. We'll bracket the -4, union, bracket the -1, up to 3, and bracket the 3. In our next example, part A is asking where is f greater than 0? In other words, where is the graph above the x-axis? That's occurring in this piece. That is from -infinity up to -2. Remember, your answer is in terms of domain or in terms of the x values. And then we're also above the x-axis in this interval, and that is from 0 to 1. Notice that we are using parentheses because of the strict inequality. We're not including those x-intercepts. Whereas in example B, we have a very similar question, but now we can ask where is it greater than or equal to 0? In other words, where is it above the x-axis or on the x-axis? We can now include those x-intercepts. So -infinity to -2, bracket, union, bracket 0, 1, bracket. In example C, we're asking where is f less than 0? In other words, where is it below the x-axis? That's in this first interval from -2 to 0. Also, this second piece from 1 to infinity. Again, we'll use parentheses since it's a strictly less than. In example D, we have less than or equal to, meaning we can now include those x-intercepts. We'll bracket the -2, bracket the 0, bracket the 1, infinity stays a parenthesis. Up next, we're looking at a rational inequality this time. Where is f greater than 0? In other words, where is it above the x-axis? This piece is above the x-axis. Again, your answer is in terms of domain or x values. So we go from negative infinity up to -1, that asymptote. And then above the x-axis in this piece, that interval is from 0 to the asymptote 1. In example B, we're asking a very similar question. Where is f greater than or equal to 0? This time we can include x-intercepts. Note that you cannot include vertical asymptotes, only the x-intercepts. So this time we have negative infinity up to -1. We cannot include the -1 with a bracket. We have to leave it as a parenthesis because it's an asymptote. Then we'll union. The 0 we can include. It is an x-intercept. Up to 1 and parenthesis on the 1 because we never reach the 1. It's an asymptote. In example C, f of x is less than 0. In other words, where is f below the x-axis? This first piece is below the x-axis, and that is starting at the asymptote -1 and going up to 0. We'll use parentheses on both of those due to the strict inequality. And it is also below the x-axis in this piece, starting at 1 and going to positive infinity. In example D, very similar question. Where is f less than or equal to 0? This time we can include those x-intercepts. Again, we cannot include asymptotes. So we have parenthesis -1 up to 0. 0 gets a bracket because it's an intercept. Then we'll union that with parenthesis 1 to infinity. Here we have another rational inequality. Up first, when is f greater than 0? When is f above the x-axis? That's in this region. From negative infinity up to the asymptote of -1. It is also above the x-axis here. That's from -1 up to 1. And again, from 3 to positive infinity. Example B, very similar to A. This time we can include x-intercepts because we have equality. Make note, you cannot include your vertical asymptotes. So we have negative infinity up to -1. We don't include it. Union -1 up to 1. This time we can include the 1 because it's an x-intercept. Then we'll union that with 3 bracket up to positive infinity. In part C, we're asking where is f less than 0? Where is it below the x-axis? In this first piece, starting at 1 up to 2. And again, from 2 up to 3. D, very similar to C. This time we can include x-intercepts. We'll bracket the 1, go up to 2, but not include the 2. It's an asymptote. Union, parenthesis 2, and bracket the 3. The steps to solve a polynomial inequality are 1. Write the expression on the left side of the inequality. 2. Find the zeros. 3. Use the zeros as boundary points to separate a number line into intervals. And then 4. Pick test points in each interval. Intervals that are true are part of the solution. For example, let's solve this polynomial inequality. The first thing we want to do is set the right side equal to 0. So we'll subtract x squared on both sides. And now we want to find the zeros. So let's set this equal to 0 and factor. we can factor out a GCF of x squared, and then set each of those factors equal to 0, and solve. The equation on the left, we take the square root of both sides, and we get x equals 0. And then on the right, we add 1 to both sides, and then take the square root of both sides. X is equal to plus or minus 1. So these values for x we will call boundary points. And we're going to put them on a number line. So we have -1, 0, and +1. Notice that in this example, the boundary points break up the number line into 4 separate intervals. We want to choose a test point in each interval and test it in the original inequality and see if it's a true or a false statement. We're looking for the true intervals. So in the first interval on the left, we'll choose, say, -2. So let's test -2. And we'll test it in the original inequality. And we're asking, is this a true statement? -2 to the 4th power is 16, and that is indeed bigger than 4. So this interval is good. It was a true interval. Next, we'll test a point in the second interval. Let's say we test -1/2. And again, we'll go back to the original inequality to test -1/2 to the 4th. We're asking, is that greater than or equal to -1/2 squared? -1/2 to the 4th power is 1/16. And -1/2 squared is 1/4. This is a false statement, so we do not want that interval. That one's false. Next, we can test a point in the third interval. Let's say we test +1/2. Going back to the original inequality, we'll plug in 1/2. And we're asking, is this a true statement? We get 1/16 is greater than or equal to 1/4, which again is false. And finally, we'll test a number in the fourth interval. For example, we can test 2. So we have 2 to the 4th. We're asking, is that greater than or equal to 2 squared? 16 is greater than or equal to 4. That's a true statement, so we're going to make a mental note that that interval is good. So the solution to this polynomial inequality are those two intervals that are true. The first interval is -∞ up to -1. And notice that we have equality, so we can bracket that -1. Then we'll union that with the other true interval, 1 to infinity. And again, we can include the 1 due to the equality. In our next example, we have another polynomial inequality. We'll start by subtracting 3x on both sides so that we can make the right side 0. Our next goal is to find the x-intercepts, or zeros. To do that, we will set this equal to 0 and factor. So there's a GCF of x. We'll factor out an x. And this time we're setting it equal to 0. We can now factor the quadratic. We have two numbers that multiply to -3 and add to 2 are 3 and negative 1. From here, we just set each of those factors equal to 0 and solve these equations independently. X is 0, x is negative 3, and x is 1. These values, these zeros, or x-intercepts, we will call boundary points. And we put those on a number line. Negative 3, 0, and 1. Make sure you put them in chronological order. Notice again in this case, those boundary points break up the number line into 4 separate intervals. We need to now test a point in each interval into the inequality and see if it's true or false. Up first, we can test a point in this first interval. Let's say we test negative 4. Negative 4 cubed plus 2 times negative 4 squared. We're asking, is that greater than 3 times negative 4? Here we get negative 32 is greater than negative 12. That is a false statement, so we do not want to keep that second interval. Make a note that that one is false. Next, we'll test a point in this second interval. Any point you want, I'm going to choose negative 1. Again, going back to the original inequality, we have negative 1 cubed plus 2 times negative 1 squared. We're asking, is that greater than 3 times negative 1? Here we get 1 is greater than negative 3. That is a true statement. Make a note that that interval is good. Up next, we need a number between 0 and 1. So let's test 1/2. 1/2 cubed plus 2 times 1/2 squared. Is that greater than 3 times 1/2? Here we get 0.625, or 5/8, is greater than 1.5, or 3/2. In this case, this is a false statement, so we don't want that interval. And finally, we will test something bigger than 1. Let's test 2. 2 cubed plus 2 times 2 squared. Is that greater than 3 times 2? Here we get 16 is greater than 6, which is a true statement. So we want to keep that fourth interval. Again, the solution are the intervals that are true. So this first interval, negative 3 to 0. And notice the original inequality is strictly greater than. We do not have equal to. That means we cannot include these x-intercepts. So we'll leave those as parentheses. Negative 3 to 0. Then we'll union that with the fourth interval, which was true, 1 to infinity. To solve a rational inequality, we first write the expression on the left side of the inequality written as a single fraction. Step 2, find the zeros by setting the numerator equal to 0 and solving. Next, find vertical asymptotes by setting the denominator equal to 0 and solving. Step 4, we use the zeros and vertical asymptotes as boundary points to separate the number line into intervals. Finally, we pick test points in each interval. Intervals that are true are part of the solution. In this first example, step 1 is done for us. Notice the left side has a single fraction and the right side is 0. We next can find the x-intercepts, also known as zeros. We do that by setting the numerator equal to 0 and solving. Take the square root of both sides. X plus 5 equals 0. Then subtract 5 on both sides, and x is negative 5. Next, we'll find vertical asymptotes. To do that, we set the denominator equal to 0 and solve. Add 4 to both sides, and then square root both sides. X is plus or minus 2. These values we will call boundary points. We'll put those boundary points on a number line. Make sure you put those boundary points in order. We have negative 5, negative 2, and positive 2. Notice that the boundary points break up the number line into 4 different intervals in this particular case. We want to choose a test point within each interval and plug it into the original inequality to see if it's true or false. In the first interval, let's pick a number smaller than negative 5, say negative 6. So let's test negative 6 in the original inequality. We're asking, is this greater than or equal to 0? In this case, we get 1 over 32 is greater than or equal to 0, which is true. So we'll make a note that that first interval is good. Up next, we need to pick a number between negative 5 and negative 2. I'm going to choose negative 3. Again, we'll plug that value into the inequality. And again, we're asking, is that greater than or equal to 0? This time we get 4/5 is greater than or equal to 0, which is true. In the third interval, between negative 2 and positive 2, we can pick 0 and plug it in. 0 plus 5 squared divided by 0 squared minus 4. And again, we're asking, is that greater than or equal to 0? We get negative 25/4, which is not greater than or equal to 0. So we'll make a note that that third interval is no good. Finally, we need to pick a number that is bigger than 2. Let's try positive 3. 3 plus 5 squared over 3 squared minus 4. Is that greater than or equal to 0? We get 64/5, which is definitely bigger than 0. So we'll keep that final interval since it's true. The solution is the 3 intervals, in this case, that work. We'll write our answer in interval notation. Up first, notice that these 2 intervals are beside each other, so maybe we can combine them. The question is, can we include the negative 5 in order to combine the 2 intervals around negative 5? Looking at the original inequality, we have equal to, which means maybe we can include the negative 5. The next thing you have to ask is negative 5 a 0 or a vertical asymptote? In this case, it's a 0, an x-intercept, which means we can include it. So since we can include the negative 5, we'll join these 2 intervals into a single interval, that being negative infinity up to negative 2. Now we have to ask, can we include the negative 2? Again, we have equality, but negative 2 is not a 0. It's not an x-intercept. It's a vertical asymptote. So we can't include it. Even though we have equality, we cannot include the negative 2 because it's an asymptote. So we will use a parenthesis here, not a bracket. And then we'll use a union to join that to the other interval that is true, 2 to positive infinity. Again, we have to ask ourselves, can you include the 2? We have equality, but 2 is a vertical asymptote. It cannot be included. So we will use a parenthesis to infinity. And we have our solution. In this example, we first want to get a single fraction on the left side. So we'll start by subtracting 3 over x plus 1 to both sides. That will make the right side 0. But we now need a single fraction. To combine fractions, we need an LCD. In this case, x minus 3 times x plus 1. The original numerator in the first fraction is 5. To get the equivalent numerator with our new fraction, we need to multiply that 5 by x plus 1. The original numerator in the second fraction is minus 3. To get the equivalent numerator, we need to multiply that by x minus 3. Now simplifying the numerator, we get 2x plus 14, and we'll leave the denominator in factored form. Now we have a single fraction on the left, and the right side is 0. From here, we can find the zeros, or x-intercepts. To find zeros, we set the numerator equal to 0 and solve. Subtracting 14 and then dividing by 2, we get x is negative 7. We also need to find the vertical asymptotes. To do that, we set the denominator equal to 0. Set each of these factors equal to 0 and solve those independently. We get x equals 3 and x equals negative 1. These are the boundary points that we will place on a number line. Make sure we put those in order. We have negative 7, negative 1, and 3. Notice in this particular example, the boundary points break up the number line into 4 separate intervals. We need to choose a test point within each interval and plug it into the inequality to see if the interval is true or false. Up first, let's pick a number smaller than negative 7, for example, negative 8. Let's test negative 8. We can test it in the original inequality, or we can come down here to this fraction, and it might be easier to test it here because then all we're asking is it bigger than 0? So 2 times negative 8 all over negative 8 minus 3 times negative 8 plus 1, and we're asking, is that greater than or equal to 0? We get negative 16 over 77 is greater than or equal to 0. That is not true. Up next, we have something between negative 7 and negative 1. I'm going to choose negative 2. Again, plugging it in, we get 2 times negative 2 plus 14 all over negative 2 minus 3 times negative 2 plus 1. And we're asking, is that greater than or equal to 0? Here we get 2 is greater than or equal to 0, which is true. In the third interval, we can choose 0 and test it. 2 times 0 plus 14 divided by 0 minus 3 times 0 plus 1. Is it greater than or equal to 0? Here we get negative 14 thirds is greater than or equal to 0. That's false. And finally, the last interval, let's test the number 4. 2 times 4 plus 14 divided by 4 minus 3 times 4 plus 1. Is that greater than or equal to 0? Here we get 22 fifths, which is greater than or equal to 0. So the solution set will be the intervals that are true. We have this second interval between -7 and -1. So we have to question now, do we include the -7 or the -1? Looking at the original inequality, we do have equal to in it, so we can include zeros because they're x-intercepts, but we cannot include vertical asymptotes. The -7 is a 0, which means we can include it. We'll bracket that. And then going up to -1, -7 to -1, can we include the -1? Notice -1 is an asymptote. We can't include it. So -1 will get a parenthesis. Then we'll union that with 3 to infinity. Again, we have to ask ourselves, can we include the 3? We have equality, but 3 is a vertical asymptote, so it is a parenthesis. Then infinity always gets a parenthesis. And we have our solution set.